I'm going to do 1,000 updates, right?
No, you will do 100,000 updates.
100,000.
10,000 updates. Because
So whatever the descent is.
you have 1,000 training data, correct?
Yes.
And you said batch size is 10.
Right.
So that means after you go through 10 images,
You're going to do the update.
you'll accumulate this, right? And then you will do the update after the 10. So if your outer loop is 100 epochs, then 100 times 100, you will do 10,000 updates, as opposed to 100,000 if it was totally stochastic gradient descent.
So it's less updates.
Less updates.
So then how does it turn to be better?
It turns out to be better because let's pretend we have some data points which are like abnormal, meaning they cause a huge gradient. Okay, so if we were doing stochastic gradient descent, let's say we are looking at the del W1, one of them may cause it to go way high. The second sample we take a look at it may reduce it way down. But in reality, even if the second one is bringing it down, the first one is increasing it, if we took the average of the two and adjusted it, it will be better. It will be slightly more stable.
So even for 100 epochs, the loss should be better for the mini batch than the SAM.
In terms of the loss.
The loss will, if you compare the stochastic gradient descent versus batch or mini batch. Okay, after let's say 10 epochs, the stochastic may actually have a lower loss. The mini batch may be somewhere over here.
Okay, because that's what I have, like with the mini batch, I have higher.
Higher, yeah.
Yeah, but the idea is as you keep going further, this will eventually become, this may start to fluctuate and may not get there.
Okay.
So it looks like we're removing the noise by taking the average.
Yeah, that's the whole idea. And that's the whole idea of the mini batch. Don't change the gradients every input you get, but take a look at the average of 10 inputs and whatever the average gradient is, then update it based on that. Okay, so now our next goal is, now that you have a basic idea of stochastic, batch, mini batch, and we decided we'll be using mini batch. Even though compared to stochastic, we may have to run the program a little bit longer, but it will give us better results, right? Next concept that I want to show you is how do we improve multi-class classification? Okay, so class, remember, in the artificial intelligence world means category, right? So, for example, if we take a look at the digit recognition, how many categories do we have?
10.
10 categories.
So that's why the number of output neurons were 10, okay? The loss function that we were feeding, so this is our loss. Okay, in the end, the loss is a scalar, just a single value, right? So let's say we fed in digit 2. Okay, this one produced 0.1, this one produced 0.21, this one produced 0.71, and so on. Okay, what is the expected output on the first line? So if I call this y of 0, if we were feeding digit 2, 0, right? Same way if this is y of 1, also 0. Okay, if this is y of 2. And so then we can do, y minus a of I squared, sum it over all. We also did a 0.5 over here to, so this is basically called mean squared loss or mean squared error. Okay, as you can see, if we pick this loss function, its job is to make the actual output, so if 0.1, 0.21, 0.71 are actual outputs, its job is to make these actual outputs come as close to the expected outputs as we keep training it, right? Okay, but for multi-class, what we ideally want to do is, we want to enhance the distinction between the true class and the class which should not be recognized. Okay, meaning, if we fed in a digit 2, we want this number to be high, for example, 0.98 or something. We want all the other numbers to be very low. For example, 0.01, 0.01, 0.05, something like this, right? So that, or let me make it 0.001, so that, so this is, if the class that's being recognized is much higher than the other outputs, then it's a lot easier to indicate, oh, it must be digit 2 that's being recognized. Okay, so anyway, so now let me introduce, so as far as gradually we'll take a look at many loss functions. So the loss that we feel comfortable so far, like I said, is the mean squared error. Okay, now I will introduce one more loss, which is called cross entropy. Okay, so especially for multi-class problems, meaning the output is supposed to be, 5 categories or 10 categories or 1,000 categories, but not a single category, not just true or false. Okay, then for multi-class classification, cross entropy turns out to be the best loss. Okay, it's defined as I equal to 1 to whatever k. So if we have 10 outputs, k will be 10. Okay, so then y of j log of, I log of a of I. Okay, so a is the actual output. Okay, so these are the actual outputs being fed in, and so and there's a negative over here. Okay. So once again, for multi-class type of problems, this is a better loss function than the mean squared error. And you will verify it through the next assignment because you'll be programming this loss function. Okay. So let me go into a tiny bit of detail of this. Okay. So far the activation functions that we have looked at. So remember, this is how a neuron goes. Okay. So f is our activation function. Okay, what are the 3 activation functions that we have looked at?
Linear, sigmoid,
tan hyperbolic,
and the linear
and rectified
rectified
linear.
linear. So
Okay. Sigmoid, if you recall, looks
0
like
to
this. Okay, tan
Minus 1 to
hyperbolic, so this is 0 to 1. Goes from
1 to -1.
minus 1 to 1, right? ReLU looks like okay. So above 0, it's linear. For negative inputs, it's 0. Okay. So as we are doing the backpropagation, obviously we need to know the derivatives of these. Okay. So for example, where was the derivative of the sigmoid?
x1 minus x,
If this is the actual output,
a1 minus f.
a times 1 minus will be the f prime for the sigmoid. For the tan hyperbolic,
Same thing, right?
it's 1 minus a squared. if I remember correctly. Okay. Or was it minus a square? Anyway, we can double check that. Okay. It was 1 minus a square. But anyway. Okay, for the rectified linear unit, it's pretty easy. As you can see, for f prime of x, for the ReLU, if x will be 1, if x is greater than or equal to 0, and 0 if x is less than 0, right? So we can easily figure out the derivatives for the 3. And in your next assignment, did I ask you to do it in this assignment or no?
No.
Okay, so next assignment you'll be actually experimenting with these and seeing which one works better for what type of.
I thought you did actually ask us.
I did ask you this? Okay, so if I already asked you this, then this is how you'll take care of it, and I'll double check on this one whether that's correct. But anyway, so these are pretty easy to incorporate, right? Okay, coming to our loss function of cross entropy.
Isn't there like a special way to do those in NumPy? Is it just kind of straightforward? You just do like tan h or?
Yeah, so the tan hyperbolic, if you recall, was something 1 plus e to the minus or something. And again, my formula may be slightly off. I think it's something like this is the tan hyperbolic. So in NumPy, we already know, like np.exp of whatever a will give you, or minus a will give you this value. So you can easily compute that in the what we call TensorFlow library, which we'll use later. These are built-in functions, but in the beginning, I'd like you to do it individually yourself. Okay. Anyway, coming back to the cross entropy, this was the loss function. Okay. So let me explain now the cross entropy a little bit better. Okay, so also let me introduce one more activation function tied to cross entropy, which is called the softmax function. Okay, so our approach will be, let's say you were creating different layers. Okay, different layers of neurons. Okay, so typically these days what we do is the first few layers, so if this is X is being fed in, this will be ReLU, or could be tan hyperbolic or sigmoid. This will be ReLU. Okay, remember the very last layer is doing the classification. So if it's 10 classes, right? So the last layer, the activation function over here, will be the softmax function. So the job of the softmax function is to enhance the distinction between the recognized class output and other outputs. Okay, so once again, you will never use a softmax function in the middle layer or in the input layer. Only in the output layer you will use the softmax function as the activation function. And what's the purpose of it? As I mentioned, the purpose is to enhance the distinction between the recognized class output and the other outputs, right? So it's a very simple function. So this is what we'll do. Okay, pretend here's our, let me make this the summation. summation over here, right? So suppose this is S1, S or S0, S9, right? Okay, so those are the outputs of the sum units. So basically the way this activation softmax activation function works is softmax function. Okay, if we feed in, let me call it S of, or let me call it softmax of x equal to e raised power, or let me call it, it's a better way to write it, okay. Suppose I feed in S of 2 as an example. Okay, so one of the sum 2 is fed in. So the softmax function will do e raised power S2. So this is what the softmax is over summation I equal to 1 to k e raised power S of I. Okay, which is, so in other words, just to see it clearly, it will do e raised power S0 plus e raised power S1 plus e raised power S9 for our 10-digit example. So that's what the softmax function does is, right? So the forward pass is easy with the softmax function. So let's take a look at the forward pass. Okay, in the forward pass, let's pretend whatever the inputs are to this S0, suppose S0 came out to be 0.31, S1 came out to be 0.2, S2 0.18, S3 0.93, and so on. Okay, so we compute the sums as we feed in the data, we get some values, right? Okay, so now what we'll do is, suppose I call this capital S, like this is the small s. Let me make the softmax function like a capital S. So what will be S of 0?
0.31 upon everything.
E raised power 0.31
Upon
divided by e raised power 0.31 plus e raised power 0.2. Sorry, there's a negative sign. Okay, plus e raised power, whatever the last value was. Okay, very similarly, what will be the value of S1? E raised power negative 0.2 over e to the negative 0.31, negative 0.2 plus whatever, okay, and so on. So if we sum up all of these, what will they come out to?
1.
They will come out to be 1. So essentially, as you will see, by taking the exponential, it's making the output, or let me make it, okay, let's make it 0.53, okay. So after we pass it through these e raised power divided by the sum of all of these, one thing that you will notice is all of these, meaning capital S0, capital S1, capital S9, if we added them up, they will come out to be 1.0. So it will become a true probability distribution. Okay. Further, you will notice previously 0.53 was the highest output. Because we are taking e raised power, then this will further become close to 0.9 something. Okay, and you can try it on some sample data. Okay. Anyway, so the forward pass is easy. We compute the sums, we pass it through the exponential function, right? And then divide by the sum of all the e raised power for all the other outputs, so that relatively we can make it bigger or smaller. Okay. Now let's take a look at how the derivative works. Okay, so let's take a look at derivative of softmax function, because in the backward pass we will be needing this derivative. Okay. So we have two cases over here. Okay, so remember SI is the input, and we will be taking the derivative, so we'll be taking the derivative with respect to Sj. Okay, so we'll take two cases when I is equal to j. And second case will be partial Si over partial Sj when I is not equal to j. Okay, so it's pretty easy to compute, because what's the formula for S of I? E raised power S of I over I equal to 1, 2. Sorry, was it a positive or was it a negative? Let me double check.
It was positive.
Yeah, it is positive. Okay, my mistake over here, not a negative, but it's a positive value because we want to enhance it. So these are all positive values over here. Okay, so anyway, I equal to 1 to k, or let me make it j equal to 1 to k S of j. Okay, so this is the summation at the bottom. This is right. Okay, so now suppose we wanted to take the derivative when I is same as j. Okay, so think of this like u over v formula. So u over v. So this will be v u prime minus u v prime over v squared. Okay, so what is v in this case? J equal to 1 to k S of j, correct. U prime, k. So suppose if you're confused, right? Pick one example, like e raised power s2. If I took the derivative with respect to s2, what will this be? The same, e to the s2. So this will be e to the si. Okay. Then minus u, u is e to the si. V prime, k. So think of this at the bottom as e to the s0 plus e to the s1 plus e to the s2 plus, and now I wanted to do partial with respect to, let's say, s2. So what will it be?
Exponential is 2 to s2.
If I take e to the s0 with respect to s2, this will be 0, right? 0. Only the term that I'm taking to will be left, e raised power s2. So this will be basically e raised power. I'm doing the partial with respect to sj, so this will be e raised power sj divided by j equal to 1 to k e raised power sj squared, v squared. Okay, so this is easy now. Okay, one of these terms gets cancelled with the square. So this becomes e raised power si over j equal to 1 to k e raised power sj minus e to the si e to the sj over. So let me break this square in two parts. So k equal to 1 to j, so j equal to 1 to k e to the s j k j equal to 1 to k e to the sj. So I basically put the square in two separate parts. Okay. So anyway, as you can see, if you take a look over here, isn't that the definition of S of I? Right? Minus, if you take a look at just this part, what is that?
It's fine.
S of I. If you take a look at this part, J, right? But we were doing this case for I equal to J. So I could write it this as S of I minus S of I, S of I. Couldn't this be written as SI, 1 minus SI? So to summarize, partial of SI, Sj, I equal to J is SI, 1 minus SI. Okay, let's do the second case where I is not equal to J. Okay, so what will this be? So again, if we go through over here, K, V is the bottom. U prime is now the derivative of this with respect to J, right? Because now remember we are doing it with respect to J. So think of it this way, this was e raised power S2, but we are trying to do a partial with respect to S3. What will that be? So for the not equal to case, what I'm trying to say is this will turn out to be 0. Okay. Because once again we are taking the derivative with respect to S of J and I is not equal to J. Okay, so this will go to 0. Case, this one will stay the same. So then what will happen over here? Because this is 0, this goes away, right? So this term goes away. So it will be simply minus S of I, S of J. So this will turn out to be minus S of I, S of J. So those are the two cases for the derivative of the sigmoid. If I is equal to J, it's SI, 1 minus SI. If I is not equal to J, minus SI, Sj. Okay? And what is this SI, capital SI? That's the output as we feed through and do the exponent, divided by the sum of the exponents of all the other inputs. Okay, so still this is not the final useful result. So now let's go to our final useful result and tie it to our cross entropy loss. Okay, so like I said, let me do this. Okay, so now let me say for multi-class problems, use cross entropy loss. So in our case, this loss will come out to be I equal to 1 to k y of I log of S of I and a minus sign over here. Okay, so now think of it this way. Pretend this is the last layer. The 10 neurons, right? Here's the sigmoid. Here's the activation function, sigmoid, activation function, sigmoid, activation function, and so on. Okay. So what kind of activation function do we have in the last layer? So this is our softmax now. And let me just put another box over here, another box over here, another box over here. Okay, so pretend it's already doing that e raised power a to the k divided by the sum of all the exponentials. Because whatever data we get, remember we have to do e raised power ai over summation e aj or something like this, right? So this blue box is essentially doing that part. Okay, so now this is feeding to our loss function. And this loss is our cross entropy loss now. And all the yi's, y0, y1 are being fed over here in our example, right? Okay, so my question to you is, in the middle of the neuron, if we compute the partial derivative, like partial L over partial, okay, what did we call this? We call this S, capital S, right? And then partial S over partial lowercase s. What do we call this part? This product. Delta, exactly. So, because we always compute the delta. Once we have the delta, then we can proceed backwards and see how to take care of that, right? So what I'm trying to say is, if I call this okay, so essentially what I need is, I need partial L over partial S of I. Okay, so delta equal to partial S of I over
small s.
okay, so let me just put it S of J over here. Okay. Or actually, let me define the delta. Let me define the delta right at the input over here. So let me leave it. So this is basically the derivative of activation function. Okay, so then this will, so now do partial L over partial SI over this one. So what will this become? I equal to 1 to k, y of I, right? What's the derivative of log of S of I?
Minus 1 by
1 over S of
S1,
I.
yeah.
So this will become over, let me just go 1 over S of I. Right? Okay, so then, so that's the derivative of this part. So this part is this part, right? Now let's go multiply by, let me just write it in plain English, derivative of